Kıymetli misafirlerimiz, 5. Ulusal Kristalografi Toplantısı'nın 2. gününe hoş geldiniz. Dear guests, welcome to second day of the 5th National Cristology Meeting. Şimdi 2. günümüzün ilk sunumu için oturum başkanı olarak Sayın Profesör Doktor Muhittin Aygün ve Doçent Doktor Resul Sevincek hocalarımızı sahneye davet ediyorum. Now, for the first presentation of our second day, I would like to invite Professor Dr. Muhittin Aygün and Associate Professor Dr. Resul Sevincek to stage as a session chair. Hocam söz sizdedir.
Morning, everyone. Welcome to the second day, the morning session. I'm great pleasure to introduce Dr. Peter Mueller from MIT Chemistry Department. He's the head of, director of the diffraction facility from 2004. Lots of things are in his curriculum vitae, but a little bit. He made his master and PhD by the supervisor of Sheldrick. Does anybody know Sheldrick? Yes. I think someone. His main goal is, I want to read his sentences. His main goal is, what is crystallography today and how can it possibly develop in the near future? I think he is thinking about the crystallography will grow and grow and grow, and I think he makes some developments on crystallography in the next future. I hope. I want to say lots of things about, but it's just let me say. So I think let's start. Dr. Peter Mueller with his speech.
Well, thank you so much. Thank you for your kind words. Thank you for the invitation. That is thanks to you. I'm very pleased. I've never been here before. Your food is fantastic. You are all so nice to me. Thank you. I'm happy to be here. And I was asked to say something about restraints and maybe get a little practical. So how do you actually refine? So this is somewhere between a talk and a workshop. Can you actually hear me without the microphone? Okay, because I don't like to be tethered. So on Friday, I took a picture in this hotel, and I brought that. So I took this picture. Oh, okay. I have 3 questions for you. First, where in this hotel was that picture taken? It is from this hotel. Second, is this pattern periodic?
Yes.
Yes, you are quick. It is periodic. Third, if so, we have figured out it is periodic. What's the plane group? What's the symmetry group? I'll leave you with that idea to think while I talk, so that if you find my talk very boring, you can think about this pattern, and at the end of the talk, we'll see whether we find out what the symmetry is. All right, back to the actual talk. I want to talk about disorder because disorder is the biggest problem that practical crystallographers face, just for practical reasons. Twinning, once you understand it, it's relatively easy. All these other things can be sorted out, but disorder is what keeps me awake, so to speak, at night. I sit there and refine disorder, that's all I do. And this sentence here, that doesn't work. This sentence here, a crystal is a three-dimensional periodic discontinuum. Discontinuum as in sometimes there's an atom, sometimes there's not. Made up by atoms, ions, and molecules. And the periodic idea means that every unit cell is exactly like the other unit cells. And of course that is not true. We've all seen that there are crystal defects, there is disorder. And in effect, you can think of 4 possible scenarios where this idea of the strict periodicity breaks down. And that is, you have more than one molecule in the asymmetric unit, Z prime larger than 1. Those 2 molecules have no relationship to one another, sometimes they almost do. Second, you have a molecule or part of a molecule show up in 2 different orientations. That would be disorder, we'll talk about that. Case 3, there is 2 orientations of the molecules that are related to one another by a 3x3 matrix. So there is a symmetry operation that changes the orientation non-crystallographically to another one. That's called twinning, and that symmetry operation is then the twin law. And finally, there is something like twinning, only there is no such symmetry operation. You have 2 distinct molecular orientations inside the unit cell, and they are not related by any symmetry. Maybe you have a molecule, you twist it a bit, and you put it back in. If it fits in the same envelope, sometimes it occurs in 2 orientations, and that I call whole molecule disorder. It is more or less a twinning effect, but it is treated like a disorder because you have no twin law, so the twin treatment doesn't work. But it can be refined as a disorder. It can be tricky, it can be easy, but so that's what I call whole molecule disorder. But for today, let's focus on just disorder. I usually explain disorder to students who have not thought about disorder before with the soldier example. I got into trouble once. I taught that at MIT, started many years ago, and then the dean of science called me to his office and said, "Peter, I've got a complaint. They complain that you make fun of our soldiers." Oh, I wouldn't, and why wouldn't? So, when I give you this example, I'm not making fun of any soldiers. No Turkish soldiers, no American soldiers. No fun shall be made about soldiers. But assume you have 100 soldiers, and they do what they do, they all look alike. And then so you can describe, as a crystallographer, this whole group of 100 soldiers like a half soldier. Asymmetric unit is 1/2, you have a mirror plane, and then you have the rule of translation, that's the lattice. And so you can have as many soldiers as you want. All you need is the picture of 1/2 soldier and your symmetry information. Okay, now the drill sergeant comes and we are raising the flag, look to the right. So the soldiers look to the right, there goes the mirror plane. Okay, now you have to describe this crystal of soldiers. It's a 2-dimensional crystal, but so what? With a full soldier, because you broke the symmetry. But now imagine, and I've seen many people who have that problem, my ex-wife, for example, they can't tell right from left. And so the drill sergeant says, look to the right, we are raising the flag. Some of them will look to the other side. The flag was up here, but what do they care? So then you have, say, 80% looking to the right, 20% looking to the left. And that's random. It's not like there's a group looking to the left and the other one. No, it's, yeah, how do you describe this as a crystallographer? That's a disorder. You can see how I get in trouble. Soldiers, disorder of the head, we are there. So you can describe this as a soldier from the shoulders down, even with the mirror plane. And then you have to give the software 2 positions for the head. And you can describe the ratio. You can even refine the ratio. 80-20 or 65 to whatever. Doesn't matter. That's a disorder. Of course, the crystal is the spatial average. You have the average of the whole crystal in just one asymmetric unit. And the software only sees electron density for both positions. So in the case of the head, is this part of this chin or part of that ear? So you also need to help the software by saying these two chins should be the same and these ears should be the same. That's the application of restraints. So you need to help the software to make sense of this blur that is the spatial average. Are you with me?
Yes.
Cool. All right, so here's the soldier. This, in fact, I believe is a gallium atom, and that's an ethyl group. And when refined anisotropically, you get this long cigar-shaped thermal ellipse. And in fact, this is one soldier looking to the left and another looking to the right, on average. And this is a much better description. Here, most soldiers look to the left, that's the solid black, and some to the right. There are different forms of disorder. The way you treat them in refinement is quite the same. You can have substitutional disorder, say all of a sudden the army allows women to fight also. And then you have these 100 soldiers, 40% are female. That's substitutional disorder. So you need two descriptions, a female soldier, a male soldier, but they occupy the same position in the crystal, in the asymmetric unit at least. That's relatively easy. Positional disorder, that's the typical case. It's either here or there. That's the looking right, looking left thing. And then mess, of course mess is not the right word, but it's often called bulk solvent, but it's really mess. You have, I don't know, maybe there's, in the courtyard where the soldiers are, maybe there's like a patch that is muddy and then nobody wants to step in it, and so the soldiers, there's no soldiers here. But there's mud, and maybe there are some dogs. I've seen bad dogs running around everywhere here, so maybe there are also dogs there, and then so there's some dogs, but every time you look, there's a different dog. So it's like every unit cell, there's different solvent. Sometimes it's pentane, sometimes it's toluene, sometimes THF, and sometimes the THF is upside down, and so there's a mess there. And you can describe that as a disorder. And so that's, in a way, it's substitutional disorder, but it's the same solvent, and it's maybe also put, it's a mess. All right. So, the refinement program needs to know the description of the two heads, or the description of where the molecules are at, or the atoms are at, and you need to also tell the software that atoms that come close in space don't necessarily bind to one another just because they are close, because some atoms are only there in some cases, and when they're not there, they're here. But these two atoms, although they're close, don't bind. And they bind, and for crystallographers, we don't think in bonds, we think in coordinates. A friend of mine once said, a chemical bond is where a professor draws the line. So crystallography is coordinates. I would actually encourage you to interrupt me at any moment if you find something funny. Laugh if you don't understand. If you don't understand, I make jokes all the time. Nobody notices. So if you think something is funny, all side. If you have a question, ask it right away. Don't wait till the end. As long as the slide is still up. So interrupt me at any moment. I won't be upset. Actually, I like it. So we deal in coordinates, and then we decide if things come close together, we draw a line here. But if one part is only there when the other is not, these atoms should not be connected. And that needs to be told to the software, and in shell X that is done with the part instructions. By default, all atoms in the crystal structure are in part 0. And they bind to one another when they come close. And then you can assign higher part numbers, part 1, part 2, part 3, and so forth. And atoms in parts with numbers larger than 0 bind only to atoms in part 0 and to atoms in the same part. So all atoms in part 1 bind to one another, if they're close enough, and to atoms in part 0, but not to atoms in part 2. While atoms in part 2 bind to all the other atoms in part 2, if they're close enough, and to atoms in part 0, but not to part 1. So that disorder with the soldiers, you just say this is part 0, and then the head is either in part 1 or in part 2, and this is not a bond. Because if this was a bond, how do you cut it? This is an ethyl group. So you have 3 hydrogen atoms here, you have 3 hydrogen atoms there. But if this is a bond, You can't calculate that. If you say this is a bond, then you have CH2, CH2, but that would be chemically difficult. So not a bond, and that's because this is in part 2 and this is in part 1. They both bind to part 0, but not to one another. But, yeah.
Is there a limitation, part 1, part 2, part 3, on usage, on practice?
I don't know.
Theoretically not.
There must be a limitation, but I don't know where it is. It is really high. I have definitely used double digits. However, there will be a slide saying that you should always use part 1, part 2 again, if you can. And I'll have a few examples. So I use part 1, part 2, and then over there is also a disorder. Again, part 1, part 2. And then the higher parts, I've used up to part 12, I think. And some things are coupled, and then this can't be in part 2, but it can't be in part 1 either. So it's part 3. And then it takes off from there, but we're talking complicated now.
Another question.
Yeah.
Is it possible whole atoms have part 1, part 2? Whole atoms are disordered?
Yes, whole molecule disorder.
Whole molecule.
It does happen. Right. Disorders involving special positions. That happens a lot. Mostly toluene does that. I don't know why other solvents don't do it more, but toluene likes to crystallize where the symmetry doesn't allow it to crystallize. Toluene is not inversion symmetric. However, toluene often crystallizes right on an inversion center. That does not make the inversion center go away. It is still there. But the toluene is then I have a slide for this one. It's a picture I took in Rome at the airport. Here it is. So if you see this kind of pattern, see there's one toluene here. Well, here's the inversion center. There's one toluene. And then the inversion center generates the other toluene. So when you see this kind of pattern of residual electron density peaks, you will, from now on, always remember, oh yeah, this is disorder toluene. And because this is a crystallographic inversion center, this disorder ratio is perfectly 50-50. But also, the green atoms don't bind to the orange atoms. So this here is not a chemical bond, this is not a chemical bond. But if we say this is part 1, part 2 is generated by symmetry. So we don't need a part 2. We actually should not have a part 2 because part 2 is perfectly generated from part 1. What do we do now? We call it part minus 1. So if there's something you don't want to generate bonds to and there's symmetry involved, make it part minus 1 and reduce the occupancy to 0.5. And those of you who have wondered, yes, of course, this is in the bathroom. So I was in Rome actually on my way to Edice, and I saw this for obvious reasons, and I figured before I use it I should take a picture, and so that I can use this for teaching. And so now you will really not forget that pattern. So whenever you see this in electron density as your peaks, as your pure peaks, it's the bathroom in Rome, or if disordered toluene, and it probably is going to be disordered toluene. All right. So instead of part 1, instead of part 1, part 2, we are using part minus 1. And part minus 1 suppresses the generation of entries into the connectivity array between atoms and their own symmetry equivalents, or symmetry equivalents of atoms that are in the same part. Make sense? Cool. And of course, you reduce the occupancy. This, the orange toluene is of course only half a toluene. Because if this was a full toluene, then you have 2 toluenes in the space where it's only enough for 1. So you need to reduce the occupancy to 0.5 for an inversion center, a mirror or a 2-fold. Reduce it to a third if it's a 3-fold axis, or a quarter if it's you get the idea. All right. Sometimes disorder involves more than 2 components. In the soldier example, we have the ethyl group point either here or there. But we could point the third way too. Now we can no longer assign one free variable and refine the ratio. Free variable, what is this? I'll show you free variable and then we'll get back to this. But if you have 2 disorder components, all you need is the ratio. 60-40, 80-20, something like that. That's just one number. 0.6, 0.8. But if you have 3 or more independent components in the disorder, you don't have a ratio anymore. You have, I don't know, 60%, 20%, 20%. And they need to add up to 1. And here you can use the sum command, and sum has a target value, a standard uncertainty, factors, and then free variables. You'll understand free variables in just a moment. So this says the sum of 1 times the second plus 1 times the third plus 1 times the fourth free variable is 1 within no standard uncertainty at all. It's almost like a constraint. It really nails it down. And that makes sure that these 3 disorder components make 1 ethyl group or 1 total order group. Sum can be used for all kinds of things, but that's one of the most important ones. If you have more than 1 disorder in one structure, there we go. So you have that ethyl group here, and then there's a disordered tetrahydrofuran somewhere else. I recommend, this is not necessary, but I recommend you use part 1, part 2 here, and part 1, part 2 there. This part 1 has nothing to do with that part 1, but the danger of that THF here accidentally binding to the ethyl is quite low. If, of course, it was, because, have you ever played the game Pac-Man?
Yes.
Of course, cool. I call this the Pac-Man effect. When you are in a crystal, you in a crystal, so you are inside the unit cell, and you reach out of your unit cell. Your hand comes in from here.
Yes.
This is like Pac-Man, that thing goes, and it touches the screen. There it is. And it's the same in the crystal. So your disorder THF down here, and your methyl group there. Next unit cell, THF here. It's the same. You can always add or subtract 1. So it could be that the methyl group bumps into this THF. And so then when the methyl group is here, THF can be there. Methyl group here, THF has to be there. So these disorders are coupled. But if they are not coupled, just feel free to use part 1 and part 2 over and over again. A, it's more elegant. B, there is a lot of software that goes crazy when you have double-digit part numbers. Nobody writing that, like, what is that that comes with the Mercury. Mercury has real problems with disorders, and if you have double-digit part numbers, interesting results are displayed. So I recommend you use part 1, part 2. Just use fresh free variables. Like that ratio, if it's not coupled, if the ethyl group disorder is not coupled to the THF disorder, use 2 free variables. That ratio, this ratio, second free variable, third free variable. Again, I will show you free variables. If they are coupled, if indeed when the methyl is here, the THF can't be here, then you have to use the same free variable because it's the same disorder. And that doesn't actually happen quite a bit when you have like an alkyl chain hexyl or something like that is floppy, and when it's here, then there is space for solvent over there, and then sometimes it crystallizes like this, and then the solvent has to be here. That is one disorder. Just 2 parts of the molecule. And you are limited to 999 free variables. The first free variable is the overall scale factor. You're probably aware that electron density, as we see it, is a Fourier summation. And all the reflections, all the diffraction spots that you collect, fancy speak for diffraction spot is structure factor. All the squared structure factors are used as Fourier coefficients. And the intensity of that spot is the magnitude of the sine wave. The frequency, what Jenny Glusker calls the electron density frequency, is a function of the resolution. The inner reflections have fewer maxima in the unit cell, and the high resolution reflections have many. It's how thinly you slice. That's the Bragg plane of business, essentially. But the phase is unknown. That's the phase problem. We are not getting to that. But now I have lost my train of thought.
Maximum number of variables. Maximum number of variables.
Yeah, the number of free. Oh, right. The overall scale factor. The intensity that you measure its absolute value is meaningless. The strength of the reflection, how strong is your X-ray source, how long was the exposure time, how sensitive is the detector, all kinds of things. Absorption, what have you. The relative intensity matters. You're shaking your head, you're not in agreement. Well, we'll talk about it later because that
Well,
will take far.
technically, if you measure F000, it would be okay.
But you can't measure it. Of course, if you measure F0, but then you will have, no. Anyway, that's coffee. Or whiskey. All right, so it's the relative, yes, please.
How about the steering hindrance between parts?
Yeah.
Is it taken into account in
No.
evaluating the disorder?
No,
Why is it not?
because we don't know where it is.
So you have no sense of.
All I have is electron density. And if I see this is here, and it's also there, then it must be there and there. And then I refine this.
Is it not possible to compute that?
You can compute it, but you cannot compute it based on the diffraction experiment. And everything I do is based on the diffraction experiment. I try to add as little outside help as I can.
And in your opinion, is it very important to take into account the still injuries between part 1 and part 2?
No, it's not.
It's not.
In my opinion, I may be wrong.
Yeah.
But considering that for 30 years I have never taken it into consideration, if I now say it's very important to take it, then I'm negating everything I did the last 30 years. That doesn't feel right. So I may still be wrong, but no, I don't think so.
I believe you.
What?
I believe you.
Yeah, I can do it. Let's rewrite Shalex, shall we? So the relative intensity is what matters, and you need a scale factor so that a carbon atom has 6 electrons or not 25. Crystallographers, I think, we would all be happy with a carbon atom having 25 electrons. What do we care? But then you have to talk to a chemist, and when you sell this chemist the 25 electron carbon atom, she gets upset. So we don't do that. So we scale everything. Just one number for all the data to scale it so that the electron density makes sense for people who are in love with their periodic table. So that's the first free variable. All the other free variables, 998, you can use for disorder. Isn't that cool? I've never used more than 20 or 30. So I've never run out, and I don't think anybody will soon. Cool. Just a little bit of nomenclature. Parameters. We have data, parameters, and restraints. That always shows up in this table. When you print it out in the end, data, parameter, restraints. And data, that's our reflections, our structure factors. Parameters is everything that is being refined by the software against the data. So X, Y, Z, for example, the coordinates of the atoms, those are very important parameters. Also the thermal ellipse, like the thermal parameters, that's the 3 half axes of the ellipse and how it's oriented, that's 6 parameters. So there are roughly 10 parameters per atom, they all need to be refined. So roughly 10. And the International Union of Crystallography feels that you should have 10 independent reflections per parameter you want to refine. It's a lot of reflections. Well, I'm not David Walker, so I won't object. I think David would. So you need a lot of reflections, and you need to be careful with what you make a parameter. I mean, we refine these atoms as ellipses. A banana would be much better, because if you have a bond and it moves along the bond, then a banana would be a good description. But a banana costs a lot of data to refine. I mean, it's not just 6 parameters. I don't know how many parameters there is for a banana, but it's a lot. So we don't have the data for it. Oh, I thought you had the number. That would be cool. So there's a bunch of other parameters that you can refine. For example, the free variables. Again, you don't know what free variables are. I'll tell you. The free variables are parameters to be refined, like the ratio between 2 disorder components. There could be BASF, that's that bit of chemical industry near Ludwigshafen in Germany. Here it stands for batch scale factor. When you look at Shalex, there's lots of jokes in there. For Shalex S, direct methods program, direct methods usually work in E space. E is normalized factor fact, let's not go there. But the way Shalex S selects the E values to use, like an intensity threshold, and that's the E value selection, ESEL, means donkey in German. So, esel is donkey. So, E value selection is donkey. George has lots of jokes in Shalex. He, of course, never says what's it, but I've asked him many things. Is that a joke? Yeah, of course. So, again, like in my talk, if you think it's funny, it probably was meant to be. Sometimes not. I still take it. So, okay, so you have lots of parameters to refine, and sometimes you don't have enough data. And if you don't have enough data and the ICR is right about that, your refinement is not exactly stable anymore. And you can use constraints and restraints to help you. Constraints and restraints are quite different. Constraints remove parameters to be refined, while restraints add data to refine against. Restraints are data. So let's do constraints first because they're sort of easier. One of the most overlooked constraints is site occupancy factors. When we say this is one atom, we are making an assumption. We are making the assumption that this atom is there in every unit cell. And we say don't refine that. It's 100% there. It's a constraint. We are not allowed. You can actually, shell X will refine it for you if you want to, but usually one doesn't want to. So that's a constraint. Atoms on special positions. Let's look at an atom in special position. Say we have monoclinic, B, thanks to Jim Ivers, B is the unique direction in, that Jim insisted on that, you know this, okay. Thanks to Jim Ivers, B is the unique direction in monoclinic, so everything interesting happens along and perpendicular to B. And if there is an atom, say that we have a twofold, that's the B direction, and we have an atom sitting on it, like so. It cannot go away from it because if the atom sits here, not on the twofold, if it sits here, then you generate the world's shortest bond. Unless, of course, you say that's in part -1 and no bond is generated. Yeah? Part -1 idea again. Paulus. Also, the shape of the atoms. If the atom is moving like this, and then you rotate it 180 degrees, that doesn't work. So if the atom truly resides on the twofold, its ellipse has to be shaped like that. And that makes it simpler mathematically. So this is no good, this is good. That means x, y, z and minus x, y minus z, that only works if x and z are 0. It sits exactly on this axis. So x and z are no longer refined. They're both 0. Constraints. Saying here, if this is your tensor, this tilt is only 0 with respect to the axis. If u2, 3 and u1, 2 are both 0, no longer need to be refined. So we have 4 parameters from this atom out of 9, almost half, that no longer need to be refined. Those are special position constraints. And you don't have to do it yourself. Shell X notices it's sitting there and just applies them. I think that was new in Shell X 97. Before you had to still set this up. Yeah, that's what it is. All right. Rigid group constraints. Some atoms can be treated as members of a rigid group, where they only move together but don't change their shape. Hydrogen atoms. In Shell X, we use the affix position. And for example, but you could for a CP, like a cyclopentadienyl, the 5-member phenyl ring, you know? It's flat, and all distances are the same. And that would be affix 5. A hexagon, benzene, that would be affix 6. George was thinking something. 5 atoms, affix 5, 6 atoms, affix 6, affix 3 for CH3 groups. That makes sense. Sulfate, phosphate ions, you can, if necessary, if the data are not good enough, you can just treat them as rigid and they can just move and tumble, but they don't actually refine. That takes away a lot of parameters, and especially if the data are poor, you don't have high resolution, maybe it's disordered anyway. This may be better than letting it refine because you can't describe this properly in the spatial average of your relatively messy electron density. Again, is this chin or is it ear? And all hydrogen atoms are, not all, but usually hydrogen atoms, especially when bound to carbon, are described, you've seen that in papers, Lighting model. Hydrogen atoms were introduced at the calculated position and subsequently refined using the Lighting model. You've read that a million times, maybe you've written it a million times. I have. Writing model means like, actually I tried this out when I was younger. It doesn't work for me, but it works for hydrogen atoms. So the idea is that the hydrogen atom is the rider on the horse, like the carbon atom, where the horse goes. Yeah, I tried this, the horse got rid of me on the bush. That was very embarrassing for me. I think the horse was happy. Can horses laugh? That one could. But that's called a riding model, and that's a constraint. Where the carbon goes, the hydrogen stops. And A fix is for rigid groups, but in shell X there's the H fix for hydrogen fix. H fix generates the hydrogen atoms and generates the appropriate A fix commands, and then everything is all set. So that is simple. There are other constraints. The more important ones are EADP, equal anisotropic displacement parameters, and EXYZ, equal coordinates XYZ. So if two atoms are smack on one another, that's substitutional disorder again. Men and women, and you don't know who's who. I figured out a method how we're not going there. EXYZ atom 1, atom 2 says these two atoms occupy the same site. Maybe one is silicon, the other aluminum. Maybe you have some strange material like one of these zeolites or so. And then you can refine the ratio, but they're in the same position and you don't allow one to go away. In that case, I would always combine that with EADP, equal anisotropic displacement parameters, because these two atoms in the same position, on the aluminum or silicon perhaps, they most likely move very similarly. And in the spatial average, you don't know which unit cell you are. They move much more similar than you can distinguish based on X-ray diffraction. So it makes sense to force them to show the same ellipse, and it makes sense to force them to stay in the same position. That stabilizes this a lot. Because the ratio between, if you have two different atoms, the ratio between is 100% correlated with the thermal ellipse, or the thermal parameters. It's a heavier atom, and you just make the ellipse larger or smaller, you can compensate. So keeping EXYZ and EADP, so keeping these atoms from behaving differently from one another, you can refine the ratio with much more confidence. And the ratio may be much more interesting than to see whether the aluminum atom moves differently from the silicon atom. So the EADP and EXYZ are often used together, but not always. You could, there's no more, CF3 groups, they like to rotate. And so sometimes you have then, well, then this is just one of the three, the other two fluorides, and then this, it's rotated on it. These two are related by something like a twofold axis along the carbon-carbon bond. And it is sensible to assume that this ellipse is the same as this ellipse. So even though EXYZ wouldn't work, they're not in the same position, EADP still does work. So two fluorine atoms of a disordered CF3 group that are on opposite sides can be helped by the use of EADP. So if you have a really nasty disorder of CF3 groups, like in these, have you ever used BARF anions? It's like you have the boron, and then it's a very good name for that ion, because if you have to refine this, it's exactly what you want to do, BARF. All right, so far about constraints. Before I move on to restraints, do you have constraints questions?
Yes.
Yes.
If you split one atom part 1, part 2,
Yep.
one atom is freely refining, is it possible to use constraints on just only one part 2?
Yes. Could be.
There's no constraint.
Yeah.
Thank you.
Anything? All right, let's move on to restraints. So constraints remove parameters to be refined. Restraints add data. This is the minimization function. So we change the molecular model such that m is as small as possible. And we do that by moving the coordinates of the atoms a little bit and maybe changing the temperature factor. And so F observed squared is our refraction patterns, reflections, that's the intensities. And F calculated is what the intensities would be if our unit cell contents were perfectly okay, so that you calculate from your structure. And the difference between those squared, that's why it's called squared refinement, times the weighting factor. The weighting factor W is in pretty good approximation 1 over sigma square of F squared. each measurement that you make as a physicist, as a chemist, as a scientist, even biologists make measurements and have standard uncertainties. Although I find that biologists don't see the necessity of standard uncertainties just as much. But everything, every datum you collect has a standard uncertainty. And if the standard uncertainty is high, that indicates that we have less confidence in that datum. So 1 divided by your standard uncertainty is a confidence factor. Large standard uncertainty, 1 over small number, you multiply. So this is our confidence. And we do this for every reflection we collected. That's what that sum thing is for. That's the minimization function in the absence of restraints. This is the minimization function in the presence of restraints. And you can see restraints have the exact same job as the data. You have a target value. This is like your observed. This is what you refine against. And then the only thing that drives me nuts is that it's called observed, because it's not observed, it's calculated. But everybody writes it like this, so what can I do? I write it like this. So this is what, yeah, that's the actual value of that parameter or set of parameters. We say this bond should be A long, and it's different, then there's a difference. And here is a 1 over sigma, just like that W, and that is the elasticity or the standard uncertainty of the restraint. If that is a small number, it's a strong restraint. If it's a large number, it's loose. You can think of it like a rubber band. And if it's very elastic, high elasticity, high standard uncertainty, then that is just a suggestion. I moved from California to Boston many years ago. California is large standard uncertainty. People are more relaxed there. In Boston, not so much. So Boston, no elasticity at all. It's almost constrained there. I like it in Boston. So that is how strong is the restraint. How important is the restraint to us? This is how well determined is this one structure factor. How important is it to us? It's the same function. So restraints are exactly like data. They are data. Only it's data that we come up with. So this is a sentence I always quote. I wrote that in the paper, I forgot which. Restraints should be used with great care and only if justified. When appropriate, however, they should be used without hesitation, and having more restraints than parameters in a refinement is nothing to be ashamed of. There is still, to this day, I don't understand it, the idea that if you have more restraints than parameters, you are over-restraining your structures. Bullshit. Nonsense. If ever you run into a problem with an editor because you have used too many restraints, like in email alert. It's almost, I mean, sometimes you have used too many restraints, and then I will tell you, but most usually you haven't. And if you use restraints with brain, so to speak, if you think about what you are doing and do it right, then the number of restraints is not that important. Of course, if you have more restraints than actual diffraction data, then it's more like a force field. But that doesn't happen often. Okay, different kinds of restraints. Geometry is always the first that comes to mind. What are the bonds? Are they the same? Are they different? Do they have a specific value? You can distinguish between direct and relative restraints. I'm a big fan of relative restraints because relative restraints only compare numbers within your crystal structure and they don't add outside forces. If you say all single bonds between carbon are 1.52 angstroms long, that's pretty close to the tabulated value, can't be wrong. But it's not elegant, and it defies the purpose of your crystal structure to some extent. You want to know which bonds are a little bit longer, which are a little bit shorter, perhaps. And if you say they're all the same, it's not so good. But you could say that all the 6 bond lengths in a Fenner ring are the same. No matter whether they are 20 angstroms or half an angstrom, you don't give any target idea. But if your data are reasonably well collected, that will come out to be quite a reasonable number. So they could be direct or relative. And if you use a really large amount of relative restraints, there is a side effect. It reduces the standard uncertainty on coordinates and then, as a result, on bond lengths and angles. And usually one would say, low standard uncertainty is a good thing, I want this, but it's artificially lower, and so the structure would look better than in fact it is. But that's really the only disadvantage I can see in relative restraints. So here are a few, because here's the workshop part. If you want to give a target value, which if you get away without better, but sometimes you have to, d-fix, distance fixed. That's the distance, that's the standard uncertainty, and then there's the atom length. Of course, you need at least 2 atoms for a distance. One atom has no distance. I mean, it has, but to what? So, d-fix 1.52, 0.02, carbon 1, carbon 2, carbon 5, carbon 7, and so forth. Gang is just like d-fix, but with double the default uncertainty. The N stands for angles. Shell X understands angles not as in degrees, but as the distance between the atoms, like it's a 1-3 distance. The bond is a 1-2 distance. Atom, atom, atom. That's the bond distance. And the angular distance here, that's 1, 2, 3 is the 1-3 distance. So, of course, you need a higher standard uncertainty, a higher elasticity for an angular restraint, and so that's why George introduced DANG. It's just the same, only it has a higher, I never use it. For distances, I use d-fix 0.02, that's default, and for angles, I use d-fix 0.04, just write 0.04 there. But in the interest of completeness, DANG also exists. But then, that's direct restraints. This is the corresponding relative restraint. SADI, same distance, I can say, oh, I have 2 arms, and distance elbow to fingers is the same on both arms. Distance shoulder to elbow, same on both arms. And that's a relative restraint. If my arms become really, really long, the restraint still holds. And if I have more than just 2 arms in the structure, maybe I'm an octopus, then there is enough stability that this is not an unreasonable result. I am a big fan of relative restraints. Same is a bit tricky. I'll spend time on same. Same needs to be placed in exactly the right position in the file, and the atoms following same have to be in the right order. There's lots of dangers in using same, but same same generates SADI. You put one same in, and it internally generates a few dozen SADI restraints. So same says that the first atom listed in the same instruction is equivalent to the first atom that follows it. The second is equivalent to the second, the third to the third, and so forth. Equivalent means this atom has the same geometry as the next. Let's do an example. I've mentioned THF so many times already. We have one group at MIT, the Buchwald lab, and they crystallize almost everything from THF pentane. Great solvents, but they tend to disorder, so I get to see it all. So this is THF, and we call these O1, C1, C2, C3, and then it's disordered, so we have first component O1A to C4A, and the second component O1B to C4B. And this is what it looks like in the file. So, one THF, here's the coordinates. Here's the free value, by the way. You don't know what free value is. I'll introduce them. And second, here's the pattern structure. So these atoms bind to one another, but not to those atoms. And vice versa. Okay. And then you say, wait, there's lots of geometry here. I mean, this thing itself, just without being disordered, is symmetric to itself. These two distances are the same, these angles, that's only that. And then the two THFs, or if you have more THFs, there are structures where like 5, 6, 10 THF molecules. They're all the same. So you introduce these two same commands. That's all you need. Same O1B, C1B, C2B, C3B, C4B. So you say the first atom mentioned is the same as the first atom that follows. So you say that O1B and O1A are the same. C1B and C1A are the same. You see where that goes. C2 is the same as C2. C3 the same as C3, and that's C4. So the two independent THF molecules have the same geometry. Yay. The second one is more interesting. O1A is the same as O1A. Trivial. But hang on. So O1 is the same as O1. And we say C4 is the same as C1. So that now means this is the same as that. But you're starting from here. So going from O1 to C1, as you do here, is the same as if you go from O1 to C4. That means these two ones are the same. Okay, continue. C3, wrong button. C3 is the same as C2. C3 is the same as C2. But you have started at 01, so now these two distances are also the same, and these two angles are the same. Then you keep going. C2 is the same as C3. Didn't we just say that? C3 is the same as C2, and now we think, is that necessary? Yes, it is. Because you're starting here, you're going that way in the file, but in your same, you're going this way. So now, when you finally close the loop, these angles also become the same. Make sense? So this second same instruction says, starting with O1, going from O1, C4, C3, C2, C1, this path is just the same as going from O1 to C4 via C1. So going this way around or that way around is equivalent. That's what same does. Yeah.
What's the difference between starting?
Well, the same generates starting. So this line of same will then say Sadi O1 C1 O1 C4, Sadi C1 C2 C4 C3, Sadi 0.04 O1 C2 O1 C3, Sadi 0.04 C4 C2 C1 C3. All this is generated, and you even find that in the LSD file. All this is generated just by this one line. So instead of you typing all the Sadis, you can just type one second. It's just for convenience.
If there is a three parts, we can't use 21 and minus 21.
No, that's when you use more free values than some.
Yes, what we can do.
They will decide. All right, and if you think this is too much typing, you can also shorten that. So this is not a greater sign, this is not a smaller sign, this is like an arrow pointing to the right. In that case down, and that's an arrow pointing up. So from O1 to C4, O1 to C4 is the same as going from O1 to C4 and then back to C1. But this is perfectly fine. If you start using same, I strongly recommend you use the long form first. It's already difficult enough to not make mistakes. This has all to be perfectly right, and the atoms have to be ordered perfectly right. If you put this O somewhere here, the whole thing will go up. Because then you are making this O the same as FC. So the order needs to be right, and this order needs to be right, and the placement, you can't put that same here. It needs to be in the right position. So there is lots of possibility of getting it wrong. So it's great, it's powerful, it's lovely, but be careful. So if you introduce the same and the structure looks really bad in the end, the conclusion is not that restraints destroy everything. The conclusion is that you haven't used them right. Right? There are others, flat. Besides the atoms that are named to be in a common plane. Mathematically, it's actually, we're not talking about chiral volume. So flat uses the chiral volume effectively to make it flat. But chiral volume is mostly interesting for protein people so that they don't get their amino acids the wrong hand. You think that's normal, but no, that happens. Right. So that's it for restraints on geometry. Time? I have one more hour. Wow, I'm not going to go through everything. That's right. Rather do a little bit right than everything wrong. So not only geometry, but also the thermal ellipsoids, the temperature factors, can benefit from restraints. We have two kinds. SIMU is just a general, really three kinds. The general similarity restraint. It says that, again, and I mentioned it a few times, in a crystal structure, we are looking at the spatial average over the whole crystal. Every unit cell is supposed to be the same, and we are seeing just the average. So if an atom that is near another atom moves in a specific way, the other atom has to respond somehow. So if it goes here, that atom has to get out of the way. So the idea is that atoms that are close, say closer than 2 angstroms, I think 1.8 is the default in shell X, atoms that are closer than 1.8 angstroms move similarly in direction and amplitude. That's SIMU. similar U is temperature factor. And then Delu and Rigu are the Hirschfeld restraints. Mr. Hirschfeld, the guy with the Hirschfeld surfaces, Mr. Hirschfeld postulated the rigid bond theory. He says that atoms that are connected by a chemical bond move the same in the direction of the bond, relative to one another. So if you have a stick and two balls, then the portion along the bond is the same. That's the simple Delu. Rigu is more modern, and Rigu also takes into account that these atoms that are on the stick should be roughly parallel to one another, so it also takes the tilt angle into consideration. The rigid bond restraints is Delu. Actually, I have a nice slide that comes later. I have a slide that shows it graphically by Thomas Schneider. Those are really sensible physically, especially the rigid bond restraints. And you can, if you feel like it, just apply it to everything. There's never a good reason not to. CMU, perhaps be a little careful, like if you have, say you have a phosphate or sulfate ion, and that tumbles a bit. Or again, the CF3 bond, the CF3 group. Can't draw that. You can imagine it. This fluorine does this fluorine does that, the third fluorine does this. You can imagine that? So it would not be sensible to assume that these two atoms move the same way. So atoms that are part of a rotating group, you've got to be a bit careful with the C move. But Rigu always works. Here's how you use it in FedEx. You type Delu, S1 and S2 are the standard uncertainties, use defaults, that's fine, and then the atom names. And C move, same thing, those are all defaults, and then the atom names. And this is the slide, Rigu, same, yeah. Oh, there's ISOR, another of George's little jokes. If an atom has such an ugly ellipse that it's a real ISOR, then maybe ISOR will help. So it's, what it means is isotropic behavior. So you assume the atoms are more soccer ball, football-like than American football-like. It's more a sphere than an ellipse. And here finally is that thing. So Thomas Schneider knew this for his PhD thesis a million years ago. So Delu, Rigu acts mostly in this direction. Rigu also angular. CMU, that's why this is a dotted line. You don't have to be connected through a chemical bond. It just makes things similar, and ISOR just makes it more balls, more spherical. And those can really save your refinement if you have poor data or disorder. Again, disorder, spatial average, you have electron density blur, and instead of having one ellipse really long and the other really small, the CMU makes them both similar, and that separates the electron density into two components. In my opinion, there never is a disorder without similarity restraints. No disorder should ever be forced to live without support from similar geometry and similar anisotropic spatial parameter restraints. Even a simple ethyl group disorder. Always give it CMU and Rigu, and the SADI for the bonds and angles. Some I already introduced to you. You can sum linearly values of, for example, free variables to a target value, which you can use for 3 or 4 or 5 component disorders. So if you have more than one component, you say 1 times the second plus 1 times the third. That goes to your question. 1 times the fourth free variable, they are 1. It's one method group that is distributed over these 3 positions. And you say the sum uncertainty is 0, so it's 1.00, but not 0.9 or so 1.1, no, 0. In older versions of the software, 0 was not allowed as a standard uncertainty, and then you would say 0.0001. So if you find old ITS files and you have sum 1, 0.00001, and then this is because 0.0 was not allowed. But ever since 2015 or so, it's fine. Okay, free variables. I keep saying we don't know what free variables are, but I'll tell you. I'll tell you now. But before I do so, I think we could all stretch a little bit, because this will require some attention. So how about half a minute or a minute of my not talking and drinking water, and then we'll go to this. It's great that you're still alive. mine, what's his name? Lee Daniels. He actually does that. I'll do what he does. Get up from your chairs. All of you. Yeah. Yeah, stretch. Turn to one another. Turn to the other side. I'm doing a Lee Daniels here. You've seen Lee
I have.
Daniels.
But it's a very American thing.
It is a good thing. Yes. I mean, this is the halfway point. I was first hours over. Or more?
We have enough time.
Oh my God.
Up to you.
I'm not getting anywhere.
Up to you.
I have so many slides. What can happen? But I think that.
Up to you.
Yeah, okay, fine.
I want to ask something to you. When using...
You should ask it publicly, so it's been better. Yeah.
Yeah, I should speed up for now.
That's what I feel comfortable. Using constraints on X, Y, Z, for example, C1 atom, can we use X as a variable dependent on X2, C2, for example, X1 is C2, X plus
No.
If it's okay, this constraint turns to restraint.
No. I don't think so.
We use it just on the flow numbers.
Maybe I don't understand the question. So EXYZ followed by two atom names, and these two atoms are then in the exact same position. That's all it does. Using the fixing the XYZ on C1. Yeah.
If it is possible to use C1 X1 C2 X plus 0.5 C2 Y plus 0.7 8 etc. Using the variable as the fixed using the variable fixing XYZ.
Free variable as a coordinate.
Yeah, you would use free variables, exactly. Yeah, and that's one of the more exotic uses of sum. Because you can then say, oh, this free variable is that free variable plus 0.8.
Can you do something for me? When you start right now, just make that out. Everyone should bring their mobile phone.
Right, cool. You've all been refreshed? Yes. Right. When you're through with me in the afternoon, Mike's talk requires you to all bring your mobile phones. Do not forget your phones to come to Mike. Right. Okay, this is going a bit into the internal workings of SHADEX. Every parameter is understood by the software as the equation 10 times m plus p. P is the starting value or the actual value of your parameter. That can then be changed. M is a number, often 0, and 10 is also a number. 10. Right. So there are 4 cases. M0, M1, M larger than 1 or smaller than minus 1. If M is 0, that whole thing is nothing. 10 times 0 is 0. And then your parameter is the parameter value and is being refined. If M is 1, then 10 times M is 10. And the parameter then appears as its value plus 10. And when the software encounters that, it no longer refines the parameter. When you see that 11 in the file, you have atom name, number, XYZ, 11. You may have seen that if you have the file structure. That 11 is 1 plus 10. It is one atom. It's there 100% of the time. I mentioned that. The site occupancy factor is constrained to not go away from 1. And so you say it's one atom, 1.0, but so that the software doesn't refine it, you add 10. And 1 plus 10 is 11. So that 11 means it's a full atom, 100% there, and don't you dare touch it. I mean, you, software, not you, crystallographer. If you want to touch it, just delete the first one of that 11, and then it's refined. Don't do it. It's getting more interesting when m is larger than 1 or smaller than minus 1. When it's larger than 1, then a free variable is assigned to So if you change it from 11 to 21, then it is, the occupancy is then 1 times the value of the second free variable. And that's just a number that you put in your inst file under fbar, free variable, FVAR, and you just put a number there, say 0.6, and the software refines it. And if you assume m is larger than 1, say 2, then the free variable is used for that. And if it is smaller than -1, then it's not 1 times the value of the second free variable, it's then 1 times 1 minus the value of the second free variable. That means the 21 and the -21 add up to exactly 1. Say the second free variable is 0.6, 60%, and you assign occupancy 21, that is then 1 times the value of the second free variable, is 0.6 atoms here, and the other is -21, that is 1 times 1 minus 0.6, 1 minus 0.6 is 0.4, so 0.4. 60/40 adds up to 1. Works every time. That's why we can refine the ratio with 3 variables. And that, of course, blows up when we have 3 components or more. So, m equals 0. That's trivial. We talked about it. This is just what I just said. But if m is 1, then you constrain things. It's a way of introducing constraints. And this is the more interesting case. So from 11 you go to 21, and you go to -21, and then these two. This is 1 times the value of the second free variable, 1 times the value of the second free variable, but 1 minus. Is that somehow okay with you? All right, cool. Those were the most difficult slides in the entire presentation, so we are done with this. This is why I wanted you to do the Daniel scans. Okay. Oh yeah, that's another cool thing. You can assign free variables to defix restraints. Defix is a direct restraint. But when you combine it with a free variable, it becomes a relative restraint. Assume that bath iron, you have 8 CF3 groups. It's a lot of CF bonds. Say they're all disordered, which is not untypical. It's a lot of disorders. And if you say all CF bond lengths are the same, SADI or whatever you use, you are generating a lot of relative restraints, like hundreds. I have no problem with that, but maybe your editor or the reviewer has. And then instead of saying SADI, all of them, you say defix, free variable, all of them. And then you refine the free variable, and that is then the CF bond distance. One advantage, you get the average CF bond distance. Not that anybody cares about it. It's disordered counter-ion. But still, you get it. With some uncertainty. Isn't that cool? Disadvantage, you have one more parameter to refine. That's the free variable. Advantage, it's relative restraints that come with the algorithm of the direct restraints. So you have fewer restraints and you please your editor. I don't care about the editor, but if I want to publish, suddenly I start caring. So here's an example. If you have, say, a ClO4 ion, happens all the time, and you want to say that all the ClO distances are the same and all the O distances, like the OClO angles, are the same. You can say SADI, Cl1O1, Cl1O2, Cl1O3, Cl1O4. And then SADI O1O2, O1O3, O1O4, O2O3, O2O4. That makes this thing tetrahedral and symmetric. But you could also say defix 21, and that, and this. And in a regular tetrahedron, the 1,3 distance is 1.633 times the 1,2 distance. So you only need one free variable for this. Then you refine it all. I recommend you do this for a number of reasons. A, it is super elegant. B, anyone who looks at that knows that you really know what you're doing, because only real experts know how to use this. And third, it pleases the editor. That's not the most important one. This is just cool. This is like one step ahead. Really, better be a bit macho once in a while. I mean, I don't have a big car, and it's that you use big restraints. Yes, it was a joke. Actually, I now do, that's a different story, but I'm a photographer, as a hobby. I run around with huge lenses now. I say, well, I'm a man and I don't have a big car. This is my lens. Now that I actually my car, okay. So now you understand this thing. You know what the free variables are. So 1 times this occupancy plus 1 times that occupancy is 1. If we have time, which I'm not fully convinced we have, we'll see. I have an example of solvent disorder where this was vital. Without the sums, it would completely have fallen apart. I think this is towards the end of the theory part. So, going back to this ethyl group, remember this slide? This is a CH2 group. CH3, this is a gallium, and this is CH2, and that's it's an ethyl group. Let's do this differently. When the CH3 is here, then the 2 hydrogens point there. When the CH3 is there, then they point here. So if you have the superposition, the spatial average, then you see that even though this carbon, carbon 12, is not disordered, the hydrogen positions on it are. This is one of the most common mistakes people that just start refining disorders make. You can tell that. You look at the paper and, I forgot the hydrogen disorder. So if you calculate the hydrogen atoms only according to part 1 or part 2, you're doing it wrong. You need to have these atoms also disordered. And towards the very end of my slides, which I will most definitely not show you, there is a structure that was published in Angewandte, and that was only one of the many problems the structure has. It was a horrible structure. I actually had to write a little paper to rebut the structure. So, get this right. It matters. So, atom C12 is not disordered itself, the 2 hydrogen bonds, atoms on it are. And yeah, as I said, this is towards the end of my, I believe you have all been given this file, have you?
Yes.
Cool. So this file in it has a PDF file that explains everything, and it has a lot of data. And what you do with the data is explained in the PDF. So this is the workshop where you sit with your laptop and you refine disorders. If you do this tonight, I'll still be around tomorrow, I'll still be around on Monday, you can ask me, but I think the PDF is detailed enough that you don't even need me. Nobody needs me. Again, the joke. So, I have 2 kids, really. So, and then I've written that little book a long time ago. There's loads and loads of examples in there, so you can do workshop all you want. So this is the theory part, and now let's go and refine this ordered solvent. I mean, I'm not really refining it, just showing you pictures. So often, if you are, I'm a service crystallographer. I run the crystallography lab at MIT, and people from all kinds of departments and research groups come with their crystals, give me the structure. And then they give me the crystal, and I start data collection, and 10 minutes later they come back, when can I publish the structure? And, data collection is running. Okay, they come back the next day, when can I publish the structure? I have problems with the disordered solvent. And then they say, don't waste time on the solvent. I only want to know what my molecule is about. What? This is Captain Jean-Luc Picard from the Next Generation Enterprise. It's a sci-fi series on TV. It's a great actor. But anyway, so here's why. So this is your diffraction pattern. This is your electron density. And here's the Fourier transformation between the two. And this is also something that has happened to me many times. People who have no idea about this, I don't blame them. There was a point when I had no idea about this. But then which of these, I can see the phenyl ring here. I think I can see the phenyl. It's that 6-member ring. And it is not that these spots here belong to that part of the electron density, and those spots over here are more this region. It's also not the other way around. Every structure factor, every spot here, is one coefficient in the Fourier summation. And similarly, every atom, every atomic position and the chemical nature contributes to the phase. There is an interconnection. Every atom has an influence through that relationship on every other atom in the same structure. If you get one atom wrong, that error spreads over the whole structure. Getting one atom wrong, say carbon-nitrogen confused or something like that, that's a small error and you won't notice. Nevertheless, you get something wrong, everything suffers. It's just like life. The Jewish people say, if you save one life, you save the world. It's the same in crystal structures. If you get the solvent right, the whole structure benefits. So that's the same for, this was for biologists, this is for physicists. It's the same thing. Diffraction pattern, electrodensity, Fourier transformation. But you can see it more closely here. Here's the coordinates, x, y, z. They're all contributing. All right, that's much nicer. So, through the Fourier synthesis, every atom has an effect on every other atom. And if we just ignore the solvent, the whole structure will be bad. And I once gave a talk a long time ago, and I called it "Truth is a Meadow," that is citing, actually it was a German philosopher and writer, and he emigrated from Nazi Germany to the US. And 2 years later, he started publishing novels in English. Pretty impressive. And he said, "Truth is a meadow, and every man picks the flower he likes best." And I thought that was perfect for crystallographic disorders, and so I found a nice picture of the meadow, and okay, then it goes dark. So this is electron density. And I mentioned there's a research group at MIT, the Buchwald lab, that always crystallizes from THF pentane. This is a structure from that group. And so the next slide will all be from that same structure. What time? How far left?
I think after almost.
Yeah, cool, wonderful. That will be handy. So, what is this? You look at this as a crystallographer, what do you do with it? I will later. Actually, in this particular case, squeeze will win.
Yeah.
But you'll see, you'll see. Okay, so I scale it differently. What is it now? Oh, it's a THF. All right, that works. It turns out this THF is actually disordered. First free variable is the overall scale factor. Second free variable takes care of this. Easy. Right. The guy who programmed the software is Paul Emsley. I think Kevin Cowden is also involved. Kevin Cowden has the exact same hairstyle as yeah, like, and apparently in Britain one says you're bald like a coot. And the software is called coot. And that's on purpose. It sounds like a joke, it is a joke. Of course, it's the crystallographic something toolkit, but they are both bald like coots. If you look up, the coot is a water bird, and they have this white thing. Right, it's cute. So, coot was used for these slides. And so that was one part of the same structure, different region. What is this? It's ugly. Yes, it's bordering on mess. But I figured I'll try pentane in here. That sort of works, but not really. So I use free variable number 3 now, because free variable number 2 I used for that THF disorder. The first one that you just saw. So this is now part 1. Free variable number 3, I assigned a value of 0.7. It refines to something like that in the end. And then I thought there was enough space. See, when you look down here, this is a pretty big bump. There's lots of electron density here, much less than there. So that's why I put the oxygen there. And so that then goes into part 2, free variable number 4.19. And there I found another pentane. That is then part 3, free variable number 5. So free variables number 3, 4, and 5 have to add up to 1.0. Because there is 1.0 molecules in this stupid cloud. So here's the sum. Sum 1, 0, 1 times the third, plus 1 times the fourth, plus 1 times the fifth. Free variable is 1. That was less easy, but still not so difficult. Okay, same structure. Oh, by the way, this is George, with his eyes almost open. And so he wrote Shell X, that's why I put that in this talk. And this, by the way, is Håkan Håkan, the father of cryocrystallography. He unfortunately has died a few years ago. That was at some ACA conference. I was the ACA photographer for decades, well, 15 years. So anyway, I like to show pictures of people who did the work, because I didn't program this, I just made the slides. So this gives you a volume of about 150 cubic angstroms, corresponds to 60 electrons if you just count 6, 12, and so forth electrons. So yeah, sure. Same structure. Same structure. Yeah. What do you think? THF? Where? No? Here.
Yes.
Yeah. Okay, THF. Part 1. As I said, you reuse part 1, part 2.
Part B is over there.
And it's free variable number 6. We are in the same structure. 5 we already used. Yes, and you think there's another THF?
Yes, part 2.
No. Part 1.
Oh.
Ha! Yes, they are far away from one another. There's no danger of them touching. Same part. But different free variable, because there's no reason why this should be just as much as that. And it sits like this. I mean, it's a 2D projection. You wouldn't see that. It sits like, when you look from the side, this is a pretty deep cloud. There's a second component to this. And that is part 2 now.
Yes.
They don't bind. And that is free variable number 8. 8. What's in the middle? Yeah, maybe. But what molecule? Pentane. We are dealing in pentane. It's the handle. You do proteins, right? But in proteins, it's always water. But here it's pentane and THF.
I'm trying to add the...
So this is not part 3 because it's not supposed to touch part 2 nor part 1.
Yes.
Part 3. But a new free variable. And of course there's one more. That is now part 4. It's not allowed to touch part 3. It's not allowed to touch parts 1 or 2. So it's part 4. And the 10th free variable, part 3. Okay. This is not stable. Or at least not really stable. It needs help with sums, not just one sum. So I use 3 sums. First one, sum 2, not 1, 2. 1, 6, 1, 7, 1, 8, 1, 9, 1, 10. So the sum of all the free variables used in here is 2. What I'm saying is, in this void, in this drawer, there's 2 molecules. 2. Exactly 2. It doesn't matter where they are. It doesn't matter whether they are THF or pentane. It's just 2 molecules. That already limits what these free variables can do. And it turns out, without that limitation, it is not. Later, okay, I'll get there one step. So now sum 1, 1, 6, 1 half, 9, 1 half, 10. So finally, these numbers are no longer 1. So what am I saying here? The free variable number 6, that is this guy, plus half of that and half of this is 1. So the combination of the two, say, this is 2 molecules, 1 half on the right, 1 half on the left. Right? This is 1 molecule, this is 1 molecule. And then finally, they're counting down. 2, 1, 0. 0, 1, 6, minus 1, 7, minus 1, 8.
Why minus?
Ha! Why minus 1? So the 6th free variable, minus the 7th, minus the 8th is 0. That means here and here is just as much THF. I mean, this is the same amount of THF as this is. So the combination of the 3, say, 2 molecules, 1 here, 1 there, and it's either THF or pentane. This last one is the least necessary of the 3. It could be more pentane than THF. The thing is, without it, the refinement wasn't stable. And it is not nonsensical, so I left it in. And this is then actually quite stable and gives a beautiful structure. A student of mine, once they saw the presentation, said, I don't think you'll need them all. Well, sure, you'll knock yourself out, I said. And actually, you don't need them all. The student was right, as they often are. It gives me actually great joy. Students are fantastic. Without them. So once the whole structure is refined, everything is done. Hydrogen atoms, there were no hydrogen atoms at that stage. You put the hydrogen atoms in, everything is refined. Then you can get rid of any of these. You only need 2. but with one it's not stable. But you can delete any of them and then the structure holds. It's a pretty nice example for structure refinement stability. Once everything is in place, a lot of things can be let loose. Sometimes you need restraints to be really strong at first, and then before you publish the structure, you relax the restraints to their default values, and it usually stays. Not always. All right, so that volume is approximately 300 cubic angstroms, and I found 120 electrons in there. All made sense. So this is, I told you that thing was deep, so I'm just showing you the same thing from two different orientations. And that's these two PHFs here, and then that's the other one from the side. And you see, it fits into the electron density fairly well. And sticks out maybe a little bit up here, but considering, this also took several days to refine. This is not something you can do in, I can do it in an afternoon now, I've seen it before, but back then, my postdoc and I were working on this for 2 or 3 days. And so without the solvent disorder refined, you could not publish this. And once you refine it, you get to an R value of 5%. That's perfectly acceptable, and it made a beautiful paper with blackboard. And R values are great, and I use them. Everybody uses R values. But a much better measure for how good the structure is the standard uncertainty and the carbon-carbon bonds. So my suggestion is, if you want to find out whether a change in your structure or model is a good one to make, don't look at the R value so much. Look at the standard uncertainties. And if the standard uncertainties go up and the R value down, the older model was better. But if the standard uncertainties go down, then you are doing something positive to the structure, even if the R value should go up a little bit because of additional restraints or whatever you may have done, or you're losing some restraints. All right. How about a void analysis? This gentleman said use squeeze. Squeeze is an old algorithm that puts like an envelope around the well-ordered portion of your structure, and then looks only at the portion of the model that has disordered solvent. And it Fourier transforms the portion that is disordered solvent, and that sort of gives you an HKL file corresponding to just the disordered solvent. And that can be used in the refinement as the solvent portion. It's called the FAB fragment, FAB. And JetX can just take that as part of the model, so to speak. So this is Tom Speck. Also at an ACA meeting, he wrote Platon, ton for ton, and Platon, like Plato, the philosopher. It's a joke. We all do this. Anyway, so it was, if you want to reward you this. Tom always looks like it's a terrible mood.
Always.
He looks like all the, he's not. He's absolutely friendly. You go to him and he never changes. Yes, I'm very happy to see you. He's a lovely young man. But at first I didn't dare go up to him. When George introduced us, that helped. But no, Tom is fantastic, and he writes that software. So to avoid analysis, this is the structure. The structure was not about solvent. This is that thing. Don't care about the solvent. The structure is actually really, really interesting chemistry. I don't care. I forgot the molecule. I haven't forgotten the solvent. Because that's where the love goes. So that's all the void that is solvent accessible. And when you look at the numbers, I know for sure you have kept tabs about the volumes that I had. Of course not. So I gave you the volumes and how many electrons. This is actually much more volume than what I considered, and it's a lot more electrons than what I considered. And in this case, squeeze clearly wins. So this is my model. Took me 3 days to do. And with squeeze, it takes a few minutes, and you get a significantly better R value and a better structure. And you see, even the standard uncertainties go down by a quarter. Squeeze wins. It's not typical. Squeeze usually doesn't win. Usually it wins very slightly or loses very slightly. Usually actually it loses very slightly. But that is artificial, because with all these parameters that you are throwing in for the disordered solvent, you are pushing down your R value. So squeeze is usually on par with lots of hard work. And remember the title of the talk, Truth is a Matter. So we're getting there. Yeah. Squeeze always works. Squeeze always considers the full unit cell, and you get everything in the unit cell, no matter the symmetry. So that's it's a good point. So these two, they are the same essentially. same volume, one more, it's giving answer. But see these positions, 0 and 1/2, they are symmetry equivalent. Yeah. Okay, so squeeze wins. But different structure, finally different structure, same research group, so same solvents. And so we have this and that. And by now you get an idea of what is happening here. You put some pentane and some THF, and that's it. All right? This is now easy for us. We've done this for the last half hour. There's the crystallographic twofold. Can you see it? So the full disorder looks like this. But only 1/2 is work. The other half is generated, so it doesn't matter. But so part minus comes into action here. This is not my point. My point is about squeeze here. So I find this volume and above 75 electrons if you just count your model. And then this is the void analysis from Platon. And I found 75, Platon finds 71. I found 320, I forgot the number, 320? 320. I found 320, Platon finds 315. The results are the same. And this is just as expected, and here, this is my disorder, 7.1, and this is squeeze, 7.4. That's essentially the same. Standard uncertainty unchanged. Only the number of restraints are much lower. There's more disorder in that structure. But yeah, I doubled the number of restraints because of all that disorder, THF and pentane. Personally, I prefer my disorder model by a lot for 2 reasons. First, I spend so much time and love doing it, so it has grown to me and on me. And second, it is more honest a model. If you, as the chemist reading that paper, looks at the coordinates, if you have all that time to download the CIF and then extract it and look at it, if you look at the model, you immediately have an idea what's going on there. While a squeeze model, that takes many more steps. So to me, if you can avoid squeeze, avoid it and put in the work. But that actually brings us to the title of the talk, Truth is a Matter. And not all flowers are easily picked. And unfortunately, the better smelling ones are harder to get. You have to climb higher to get just this one flower. But the easy flowers smell good too. So that's the squeeze, the non-squeeze thing. So the easiest are pretty, and all electrons matter, and nobody should be without flowers. And so those are the slides I won't show you. This is what it looks like when I look at it. Beautiful. So we have like 15 minutes left to talk about things. And if one of the speakers doesn't show up, I can show you your slides at a later time, but I think I've pretty much saturated you anyway. These are restraints and constraints in this order. On a couple of examples, you have the zip file where you can get your own practical work in, and go for the flowers. And if you have questions, please do ask. For example, now you had a question. What you answered?
No.
Okay.
Yeah. The zip file contains the previous examples you and your PhD students solved.
I'm not sure whether that structure is in there. I would have to check. But if you want the data for the solvent disorder, just ask me. I have it somewhere. I think that's a separate workshop, but I can make it available.
Okay. If
It's-
I cannot find, I will ask you.
You will ask me, and I'll
Right.
write it. But there is in that file is a really difficult disorder with crystallographic symmetry. So it's a disorder, and there's a twofold axis that goes right through it, but it's not necessarily a 50-50 disorder. So these two things are completely independent of one another. It's really cool. That was for a long time the most difficult structure I did. And actually, I dreamed the correct answer to this. This has never happened to me before or after. I was working on this structure for weeks, easily 6 weeks, for many weeks. And 6, maybe 8 weeks, I gave group meeting on that structure, and I couldn't get anywhere. The structure solution was obviously correct. You can tell from the statistics, and there were atoms, and they all seemed to make sense, but they didn't make sense chemically. And I worked every day on this, and George Shelby looked over my shoulder, yeah, this looks right, but yeah, that's all wrong. And at one point I woke up at 3 in the morning. I know what it is. I hopped on my bike, I biked up to the lab. By the time George got in at like 8 or something like that, I had it all figured out, and then I went back and took a vacation for 3 days, and then I rolled it all up. It's once you have the idea, it's obvious, but that's in the file.
Is there a question? Suggestions?
I'm not special in this area,
Yeah.
but is this program similar to breakdown refinement table?
No. Liquid refinement is based on powder data, and you need a lot more assumptions. It's single crystal. It's a single crystal. And if you have a lot more data in single crystals, it's no overlaps. It's a different approach. Yes, liquid refinement is a powder method. And shell Excel is a refinement software for single crystal data, where you have individual brand potentials. So, yes.
Mikrofon verebilir miyiz arkadaşlar? Mikrofon.
I'm wondering what's the difference between protein crystallography disorder or chemical crystallography disorder definition?
It's a great question, and the answer is simple. There isn't one. It's the same thing.
Same thing. Because when we have disorder in protein crystallography, we don't see anything in the electron density map. But can we say the disorder in chemical crystallography is like the different populations of ordered things in the same solution?
I don't understand.
I mean, can we say the disorder definition in chemical crystallography, the different populations of the ordered structures in the same solution, in the same crystal?
You mean how much of the molecule is disordered?
Yeah, or in different occupancy maybe. Because in the, as I say, in protein crystallography, when we have disordered parts, region, we don't see anything like any electron density. But you see something, right?
Yes, I see something. Yes. Okay, let me rephrase my first answer. There is no difference. However, in protein crystallography, you are usually facing much more severe disorder.
Yeah.
It often involves water, and you have low resolution data, and you just see a lot less. Everything moves more. Even the ordered portion of the protein moves a lot more than the ordered portion of the small molecule structure. So it's exactly the same as it is for small molecules, just much more difficult. You need a lot of imagination to see the other components, and sometimes you just can't see it.
Yeah.
And if you can't see it, you can't model it.
But yeah, and also it's a danger to have too much imagination when you interpret.
Yes, I have been accused of that.
No, I'm saying for protein crystallography.
Yes, you can have too much.
Don't model when
Yeah.
you don't see anything.
Yeah, I would then not model it, and maybe comment that this looks like you have high B values for some of the means, the acid side chain, and yeah, there's motion, what can you do? So sometimes a large thermal parameter is just as good as several components.
Yeah, thank you.
Of course, you're welcome. Thank you for the question. Of course.
Which software do you use on studying disorders? Which software?
Shell Excel.
Shell Excel.
Yeah. The refinements. Oh, you mean for visual?
Yes, visual.
Yeah, yes, I admit I use XP.
No. I don't know anything about XP.
XP is old. I mean, there was an operating system, Windows XP. When XP was written, there was no Windows.
Yes. I know.
The mouse had not been invented.
Just only typing.
Only typing.
Like MS-DOS or...
Yes, exactly. And everything is 4-letter words. Every command in XP is a 4-letter word. You need to know ahead of time what you're using. So when I teach crystallography, I force my first students to learn XP.
Yes.
Because they have to think first before they get anywhere. If you use something like Shell Excel or OLX2 or something like that, you can click, and all of a sudden the molecule looks good, and then you think, oh, I'm done with the structure. And oftentimes you are not.
Yes.
You may even have dug yourself a really deep hole, and you're sitting in a pseudo-minimum, and the structure looks good, but it's wrong. In XP, that does not work, because before you do anything, you have to think what you want to do.
You write your
Yeah.
two 1.0s minus two 1.0s.
These things.
But
And so it is really hard for the first 2 days. But after 2 days, everybody gets it. I have not seen anyone who would, after 2 days, not use XP then almost normally. And I teach that class at MIT. It's a full semester course. And the first week or so, people struggle and they, oh, why does he do this? And oh, it's terrible. But after 3 weeks, like, oh yeah, type this and that. And then they start yelling XP commands across the room. It's a really fun program, and it's very powerful. It's very fast. It doesn't make any mistakes crystallographically. And you get exactly what you want and not more.
Thank you.
And so George wrote it, and I got my PhD with George. And so this is what we all use, and I'm so familiar with it now. One of my postdocs was using Shell Excel, and I raced. We collected new data, and we started with the HDL file at the same time. We started the clock, and I did everything with XP, and he did everything with Shell Excel. He won, but not by much. So naming atoms in XP is really tedious, and so that is what held me back. But I caught up because the refinement is much easier. But you have to get used to it. So I use XP, and I'd be happy to teach anybody who wants to how to use XP, but it's hard at first because there's barely any documentation available, and it's a lot of typing, and there is no mouse. I mean, there is a mouse, it just doesn't do anything. You know. It's all typing. All right.
Any questions?
Yes.
In the quantum crystallography field, there is some advanced technologies to characterize the electron density
Yes.
more sophisticatedly.
Yes.
Do these also help with crystallography findings?
Theoretically, yes. It depends on what software you use. If you use the common software, what is that called, XD, it won't really work. But Mueller, that French guy, what's his name?
I know Nostara 2 works with disorder.
So in Mueller it works. I mean, the software can do it. The thing is, it becomes a lot harder theoretically to describe bonding electrons when there's disorder. There's too much disorder going on to see what you're after. So I would be cautious to interpret too much into a quantum structure that is based on a disordered crystal. But I think it is mathematically possible. But the results are trustworthy, I doubt, but I don't know. I don't do this much. All right, should we look at the
questions, suggestions?
Thank you very much for this interesting and exciting presentation. I wanted to learn, I'm the director of the graduate school in Ankara, Gazi University. I wanted to learn how do you integrate these interdisciplinary programs in crystallography. So you have students from biology, physics. Is crystallography a program, an international undergraduate or graduate? In which programs do you teach crystallography? Undergrad or grad?
My courses at MIT are graduate classes, but there are
My course is undergrad.
there are often undergrads coming. So it's not that they are not allowed to come, but it's part of the graduate program. And I get biologists, physicists, material scientists, and chemists.
Is it a must course? Or
No.
elective course?
It's maybe good.
You have students from both students and
Yes.
biochemistry.
Yeah. If they're interested, they come. And I have two courses. One is a half semester, that's the theory. Then I have a full semester, that's structure refinement. And that full semester is 6 hours every week. No, 5 hours every week, and whole semester. And we refine different structures.
Thank you.
Of course, thank you.
Any questions?
Time for coffee.
Thanks to Dr. Peter Mueller for this